Okay, so we'll be slowly proceeding to the next talk by Pau Fonseca, as you see. The title of the talk is Using a Digital Twin to Forecast the SARS-CoV-2 Spread in Catalonia. Pau, whenever you want.
Okay, thank you for the introduction and for the opportunity to share this talk. First, I want to explain why we are starting working with this kind of work. For years, we are working in simulation in LabFIP, that is a research institution located in Barcelona, in Catalonia. And we are working in simulation mainly focused in industrial area. But time to time, we're moving to environmental area because in the frame of Industry 4.0, more and more is needed to include elements related with the sustainability and so on. And for that, we are naturally moving to the environmental area, starting with the simulation of wildfires, snow avalanches, and other type of phenomenon that are more related with environmental conditions. From that, we are start moving to social simulation because the behavior of humans is really relevant in how, as an example, a building is going to behave, the energy consumption in buildings and so on. That is an area that we are actively working right now. And for that, we are moving also to social simulation. When the pandemic situation starts, for us was very natural to start a framework to try to predict what will happen in the future forecast in Catalonia. And this is what we do. Okay, from the beginning of the pandemic, we start defining a digital twin that is mainly a replica of what happens in that case in Catalonia, focused on this spread. This is the outlook that I'm going to follow. First, I'm going to explain what is the project. I will be detailing what will be the validation and verification loop that we are going to follow. This will be really relevant because it's the core of the methodology that we're using. It's a methodology that insists on the idea that we are working in a digital twin, and for that, a digital twin is going to live with the system. I'm going to present what is the idea of digital twin that we're using and some results that will be of really interest in the current situation that we're facing right now. Well, this is the name of the project. It's Pandemic Simulation to Test the Effectiveness of Containment Strategies through Cellular Automata and Intelligent Agents using Formal Languages. It's a long title, but the idea is that we are going to try to test if the non-pharmaceutical interventions, that is to use face masks, social distancing, and so on, is effective in order to make the containment of the pandemic, of the spread of the virus in the case of Catalonia. For sure that this will be also applied to other communities or countries. Okay, but we are focused in Catalonia because we are using this data for validation. For that, we are going to have one important goal, that is to model, to show, the model is wants to show a pessimistic scenario with the maximum number of cases. For that, we are going to be focused on what is the worst case scenario that we are going to face on. And because that, I want to show you right now, we are going to see that the forecast is over all the different cases. This is the natural goal of our project, okay, to forecast what will be the future trend of the pandemic situation in Catalonia and so on. But the more important goal is the first one. This project aims to become a minimum viable digital twin of the Catalonia pandemic situation to change the discussion version of models. The idea is that in the frame of Industry 4.0 and the complexity of the problems and situations that we are facing right now, the pandemic situation, the climate crisis, and so on, more and more is absolutely needed to discuss based on models. What is that? Well, the idea is that instead of working only analyzing the data or analyzing the ideas or the preconceptions that we have, we need to define models that, based on the information that we have in the data that we have, test that if the things that we are understanding or thinking are correct or not, to try to understand the causality of the things. It's a new way of thinking that is strongly based on the ideas of Industry 4.0. And this is one of the main goals of our project, because we're working with the health department in order to try to explain how important it is to start talking based on models. If you have an alternative, first, you need to test if this alternative is working. This is the team that are right now working on this project. And at the beginning, we are more people that are focused on the validation area. Now we are the core engineers that are working in this and data scientists that are working in this project. And also with the collaboration of the CANFI, that is the Societat Catalana de Medicina Familiar y Comunitària, that are working in the first line against the pandemic situation, so that they have strong information, very, very deep information of what happens in the health system, and they are providing us insights, information, and also working with us in the validation of the things that we are looking at every day. Well, what will be the approach that we are following? The idea is that we are going to discuss we're going to work in discussion based on models. And the idea is that we are going to work in a validation, verification, and accreditation loop. We are going to do continuously the loop that is represented here, that I'm going to explain just a little right now. We are going to do this continuously in order to assure that the assumptions that represents the causality of why the things happens are true. Okay. For that, let's go to see what will be this loop, and let's go to be focused on different areas. First of all the models that we are going to use in any ambit are going to be defined because a goal. For that, first of all, we have, let me check if I can take this. We have a goal. Okay, display settings are options. Visible. Okay. Okay, here we have the goals that will be the things or for what we are going to build this model. In our case, we want to forecast the worst scenario for the spread of the virus in Catalonia. For that, we are going to define the problem entity. The problem entity will be the area that is going to constrain what is my system. As you might imagine, if we want to model what will be the spread of the pandemic situation in Catalonia, we want to start modeling what happens in Wuhan, in China, okay? But this implies that we need to include information regarding Wuhan, number of people, the behavior of these people, the non-pharmaceutical interventions applied to these populations, and so on. For that, we are going to use the information of Wuhan. Wuhan is not in our model. Also, France, Italy are not in our model. For that, the problem entity will be the constraint, the area that is going to be focused, that we are going to be focused, is my model. For that, definition of the problem entity is quite important. For this, obviously, defining that implies that you are applying some kind of assumptions. And these assumptions implies that, as an example, that you have some rule that allows you to introduce information regarding how the different infections are going to come from Wuhan, from Italy, from France, and so on. Okay, but you are going to use these simplifications in order to make your model useful. Okay, because in any case you are not going to have time to validate all the things. With this, you are going to define the conceptual model. The conceptual model will be, as in our case, a set of graphical charts that can be understood by everyone, that contains all the assumptions that we are going to use in our model. For that, with this conceptual model, we can start doing something that is named the conceptual model validation. The conceptual model validation is, okay, let's go to see the graphical relations that exist in my model in order to understand if everybody of the people that are going to do the validation and the model construction agrees that the things are working like I believe that they're working. Okay, for that, the definition of a conceptual model is a key element, because it's going to become the common language that everybody is going to use in order to execute and understand this model. From this conceptual model, we are going to do a coding, and we are going to obtain a computation model, codification, an implementation of this model. And for this, we are going to be able to do some kind of executions throughout the scenarios configurations that are going to be validated also, okay? And for that, we are going to obtain some kind of solutions. These solutions that we are going to obtain can be tested with the real thing that we're analyzing, that in our case is the spread of the infection in Catalonia. This is named the operational validation. It's another important validation, because here you are going to see if the number of cases that you have in Catalonia are more or less similar to the cases that your model is predicting. Okay, so that this is a very important validation. Another important validation is the data validation. The data validation is going to assure that the information, the parameters that you are going to use in your model are going to be correctly used. As an example, in a SEER model that I'm going to present next, one important parameter is the beta that defines the propagation of the spread of infection. For that, in that case, this beta needs to be tested. Okay, this testing is going to be done through the data validation. Finally, once you have the solutions, you are going to think that you have a forecast and you want to see, okay, this forecast is very bad. Let's go to see what are the non-pharmaceutical interventions that we can apply in order to reduce the spread of the infection in Catalonia. Okay, in that case, you can test several different alternatives, and then from all these different alternatives, you are going to select one alternative. That is, okay, let's go to apply this non-pharmaceutical intervention to the population. Let's go to see that no, everybody is going to go home at 10 o'clock. Okay, this will be a non-pharmaceutical intervention. For that, you are going to accept one solution, and from this accepted solution, you are going to see what happens in the system. The models say that applying this non-pharmaceutical intervention, something is going to happen. And then you are going to see if these things that is predicted by the model happens in the system. And this is the solution validation. Solution validation is the more important, or not the more important, but is the distinctive validation that is going to be done in the frame of Industry 4.0. Because solution validation in the frame of Industry 4.0 is going to be done continuously. The digital twin is going to exist along with the system. For that, if the system exists, the digital twin is going to exist. For that, while the system exists, the digital twin is going to exist, and you are going to continuously doing a solution validation. Okay. This will be the overall perspective. There's more details on that, but the important thing here is that this is a loop. We are going to do continuously this process of validation, verification, and so on. And we are going to assure that through this validation verification loop that we are doing here, the assumptions that we are using that expresses our causality are correct. Well, here you have how we are doing these different validations. For the part of the operational validation, is assuring that the results that we're obtaining are correct from the coding, from the implementation of the models that we have. In our system, we are doing three different implementations. The first implementation was done using system dynamics, a typical SAID model that I'm going to present you next, and has been implemented in SaveMaker. Okay, for that, this is the first approach. From that, we are doing a second model. The second model is using Python. In this second model, we are using optimization in order to select the turning points. The turning points is a curve that represents the spread of the infection, okay, how the cases are going up and going down and so on. In this curve, you will see turning points. We need to detect what are the minimum set of these turning points that allows us to detect what will be the beta for the past. Okay, and with this, we are going to try to we predict the future. This is going to be done in Python. The relation between system dynamics model and Python model is very obvious. The results are going to be the same, exactly the same, very, very coherent in the assumptions, and also exactly the same solution. The third model that we're using is the L model, Specification and Description Language model. It's a model that allows us to increase the power, the semantic power that we have in our model. The semantic power will be increased because, as an example, we want to add information regarding the vaccination process. We want to add information regarding of how long the protection of the vaccines last. Or as an example, we want to add information regarding the new variants of the virus that can appear. All this information is really complex to be added in a pure system dynamics model, so Python model. We can do that, but implies strong modifications in the models, and for that this implies that if we need to do the operational the solution validation, that remembers that is going to be done continuously during the system life, implies that we need to add a lot of effort. In contrast, in SDL model, this is going to be easy. Okay, for that we are going to implement all these refinements in the model in the SDL model. If the codification is going to be correct in all these different implementations that we have, we expect these coherent results, and this is done. When we have these coherent results, we finish the operational validation and we go to other validations. This is the initial shared model done in SageMaker. If you are not using with the shared model, just to mention that in this kind of models, we can imagine that we have an analogy of the people, the population, like water. Okay, the water is going to flow through all these different containers, and the containers are going to represent the different stages of the people regarding the disease, the split infection. Susceptible people are going to represent the people that can be infected. Exposed are the people that are currently infected. Infective are the people that are infected and also are spreading the disease. And then you have dead people and recovered people. Okay, so that this will be the different stages, the different levels that we can have in this kind of model. This is a preliminary model. As an example, this is the first model that we do in order to predict what will happen the wave in Catalonia if nothing happens. Okay, it will be absolutely disaster. If we didn't do nothing, it will be an absolute disaster because this is very, very high. Okay, well, this is the equations, the differential equations that rules the behavior of this fluid, this liquid that is moving through the different compartments that we have in our model. This is the initial model. The rules of this model are used in the Python model and also in the specification and description language model, but the way to define these equations is a little different, but it's the same. In the specification and description language, the definition of these equations is not done through differential equations, but through graphical diagrams that expresses the same thing. Well, the same thing, no, because in the specification and description language, we add more detail, more complexity, but we can detail and express the same thing. Regarding the verification, I want to mention that we often talk regarding validation. Validation is understand that the model is correct. Verification is understand that the model has been correctly implemented. And in our case, the verification has been done strongly on Python, but in the system dynamic model, the implementation has been done through SageMaker that assures that if the drawing model is correctly done, then the implementation is going to be done correctly. And in the case of SDL, we are using SDLPS, that is a software that we are using for in our group for research that assures that if you draw a diagram expressing the relations of the model, then the codification, the implementation is going to be correct. And for that, the verification is simplified largely in the SDL model. That is one of the things that we want. I'm not going to enter more in details of this conceptual model validation. It's just to assure that if you are going to see the representation, the graphical representation of your model, then all the experts are going to agree that this graphical representation expresses the relations between the things. To do that, we are using SDL language. SDL language is an E2T language, it's a standard language. And it's a language that can be used also to express cellular automata, multi-agent systems, and so on. The truth is that in our model, we're using cellular automata in order to represent the different health regions that we are finding in Catalonia. Currently, we are working with GICRA, that is a research center for water, in order to test what is the number of viruses that are going to find in the water. And also, we are extending that using cellular automata. We are not using yet multi-agent simulation because multi-agent simulation is going to provide us more detail. As an example, if you want to model what happens in a room or wherever, we are not doing that. But with SDL, we can do that. Okay, we can extend the model to cellular automata, as we are using right now, or multi-agent simulation. Well, this is the website where you can find SDLPS, and you can download it. You can use it for your purposes. It's a research tool. If you want to use SDL for modeling and SDLPS for the coding, for the codification implementation of these models, use enter into the website, contact with us, and we are happy if you want to use. Well, this is SDL. Notice the idea that everybody that is going to work in a definition of model like this have different ideas of how the things are working. And SDL, this is a definition of the model in SDL, is going to define specifically how the things are going to work. For that, everybody must agree that this is representing how the model is going to work and how the assumptions are going to impact in the behavior of the system. That is the number of new cases that you are going to find. Here you have, this is really small, sorry, but here is susceptible population, exposed population, infective population, infective detected population. We distinguish between the detected population, infective detected, and infective real infective population. Dead, recovered, and also be confined. That is a block that is going to help us in order to express the different non-pharmaceutical interventions that are going to be applied. Well, finally, the data validation assure that the parameters are correct. Every one of the different blocks that you have here are going to be detailed more inside the SDL language. For that, finally, you are going to understand what will be, as an example, the beta for the propagation, and this is going to be done using normal statistical techniques or data science techniques that you might know, in order to assure that this beta is correctly used. Well, this is just an example for Python for the first analysis of beta. We don't have information at the beginning, the first wave, and for that, the things that we do is just to analyze what happened in South Korea, what happened in Spain, using the Python model to do this fitting, and with the optimization model in order to find what will be the way to find a curve that follows exactly the points. As you can see, using one point of inflection, one change point is, in the case of Korea, it fits well. In the case of Spain, we need 2 inflection points or 3 inflection points that are representing maybe the non-pharmaceutical interventions that are going to be applied. Every time that you are applying a new non-pharmaceutical intervention, you have an inflection point, a turning point. For forecasting, if you don't have historical data, one of the things that we do is compare with other system approach. That is another approach that can be used in data validation. That is, okay, let's go to see what happens as an example in Israel. And then we are in this situation in Israel, exactly the same incidence for 100,000 people. We are here in Catalonia. We expect to find this kind of behavior because the non-pharmaceutical interventions are applied in the both populations are the same. And just to mention that exactly this happens. Okay, we are able to predict perfectly the second wave using this kind of approach. For the next waves, we have information regarding the betas. And for that, for the next wave, we are not using more this approach because we have enough information in the data set of Catalonia in order to understand what happens if we are opening the bars, closing the theaters and so on. We have information of that following what happens in the past in Catalonia. For that, right now, for us, it's quite easy to understand what will happen if something happens in the population and so on. This is the approach of the digital twin that we are following this validation verification loop. And this is the idea of a digital twin. I want to mention just quite faster here that a digital twin is going to do a comparison between a digital shadow. A digital shadow is something that is going to represent information, the data, and digital shadows from simulations. This digital shadow is going to come from the simulations that you have in your models. Here you have different models. Okay, in our case, we have 3 different models. We're using these 3 different models to obtain digital shadows from simulations. We compare this with digital shadows from the reality, that is the real cases that we have. And then here we are doing this validation. So for that, the idea, the concept of this approach is very, very common in a digital twin approach. This continuous validation is what we are mentioned regarding the solution validation. Okay, the continuous solution validation that we are doing in this approach. Okay, doing that, finally we have different models. In the website you can find the different models that we do. The model invalidates. A model is going to invalidate always because the system is going to change. As an example, look this huge slope that we have here. If nothing has been done, a lot of people is going to die. For that, obviously something is going to be done. People is going to here we close the people, we close the bars and restaurants and and the nightlife and so on. And because that, this is not going to go up, but going down again. Okay, for that, every time a non-pharmaceutical intervention happens, the system changes, and for that we need to change the digital twin that represents this system. And this is just a representation of the different digital twins that we have, past digital twins that we have that are not correct because the system changes. And because the system changes, we need to change the assumptions that we're using the non-pharmaceutical interventions that we have. The results that we are finding using this approach are very, very interesting, because as an example, here you have this table that has been published in a journal recently that expresses what is the beta, okay? This is the slope that we are going to find depending on different non-pharmaceutical interventions. So that is what's quite interesting, that when the government of Catalonia gave free masks to the people, this has an effect over the population. Remember that is at the end of the confinement, everybody leave again from home, start to moving in the streets, but the people are more or less afraid. The people are using the face masks that the government provide. And this causes an effect on how the infection is spread. Other examples that happens is reopening the restaurants that have an effect, the school returns with the returns to home and working and so on, that also have an effect. And we have very, very clear that every time a non-pharmaceutical intervention is applied, beta changes, and we are able to quantify how this beta changes. With this information right now, we are able to predict what will be the future forecast for Catalonia. And this is, as you can see here in this chart, what will be the future forecast for Catalonia. This is what you can find in the website. You can see what is the real number of cases. This is the detected cases. This is the real number of cases that we have right now in Catalonia. And this is the forecast. The forecast have two lines. First line, the green line is the detected cases, and the orange line is the real cases, okay? Because we have a lot of people that are symptomatic, and for that they spread the disease without understanding that they have the disease at all, okay? This is the forecast that we have right now. Always when we are facing a change of trend, we define a forecast, and in our experience, we are able to predict successfully the second, the third, the fourth, the fifth wave, okay? Obviously, this model, I think that is not going to be true, because if we are at this situation, something is going to happen. Okay, as an example, now we are going to make mandatory the use of face masks in interiors and something like this. Okay, so that if something is going up, then the competent authorities is going to do something that makes that this is not happen. Okay, but if nothing happens, this is going to be the thing that is going to happen in Catalonia in the near future. Okay, and as a conclusion, because it's more or less time for 5 minutes for any question that you have, the proposed methodology that we are following defines a digital twin of the pandemic and must serve in order to facilitate the pandemic evolution monitoring, in order to see what will be the future of this pandemic situation, providing early warnings. Notice that the model that I show you right now has not published now, but has been published 5 weeks ago. 5 weeks ago, we know that we are going to face right now a rise in the cases, okay? Because we know that if some non-pharmaceutical interventions are going to be avoided, then this growth is going to happen. The situation right now is that the growth is very slow, so that is a little more complex to detect that this is an exponential growth, but this is an exponential growth, as usual. Okay, the comparison with the shadows. In the context of Industry 4.0, the model-based discussion becomes a central element to understand the causality of complex systems. This is a really important message of this project. The complex problems that we're facing needs a discussion based on models. And the continuous validation of simulation models, which includes a clear representation of the causal relations, is part of the proposed methodology. Validation, continuous validation is going to be important. It's going to be needed. Without a continuous validation, the models are going to be not useful for making decisions, okay? And that's it. If you have any question, I will be happy to answer to you.
Thank you very much, Pau, for such an interesting and maybe polemic talk. Is there any question, comment, remark? No questions? I would like to ask something about you already commented it, but you could comment a little bit more on the fiability of prediction in some sense. You said that those two curves.
Yeah, I will show you because I prepared here. I think that you can see now, this is the website that you can access right now. Okay, and this is the model. Let's go to see just little detail of the indicators that we have here. Okay. The indicators that we have here are effective growth, that is no metric that we have, that is expressing the trend, how we are, what is the direction that we are facing right now, okay? And what is the strength of this direction? The first one, that is C3, have a strong bias. But we want to keep this with this strong bias because it's going to help us in order to detect an early warning. Okay, in that case, notice that we have 1.2, 141, 1.3. The problem is here, this value of C7, that is the mean of 7 days, is bigger than this mean of 14 days. This implies that we are going up. Okay, so that this is suggesting that we are in the bad direction. In the other side, we have the incidence. This is the incidence that we know for 1,000 people. This is again strongly biased, okay, but it's an early indicator. And here we have the value for incidence of 7 days at 14 days. This is showing us that we are not at the top of the curve. This information is going to be used along this, that is the forecast, okay? We are going to see in detail if the green line is going to go over the observations. The observations are these, that are the real cases that are provided by the health department. With this, we're going to be able to detect if this green line that we have here is following exactly this. If this green line is navigating over these observed cases, because the nature of the pandemic is spread, for sure that the trend is going to be like this. Not only because this is following this kind of behavior, but because all the other waves that we're facing right now are following this trend. Exactly the same. Exactly the same.
Okay, thank you very much. May I ask another short question, because it's almost time, which is about cellular automata, about the representation you were talking about cellular automata. Cellular automata is a cellular automata, I mean geographic, spatial, or related to variables of the model?
Good question. In this panel that you have is geographical. Is related to go to the health regions. Okay, this is the health regions that you have. We can go to Barcelona, and then here you are going to see the representation only for Barcelona, and this is a cell of the cellular automata, only for Barcelona. Okay, for that is geographical. But in the case of the ICRA, it's not going to represent geographical situation, but information related to an area. I don't know what is the name. A water purification resource.
Okay.
So that is not a geographical area, but it's a variable, because a lot of different geographical areas are going to be supported by this structure, by this infrastructure. Okay, and it's a variable in that case. But this is not published yet because we are working right now on that.
Okay, thank you very much for answers. Thank you very much. It's time to close this Minisymposia. I want to personally thank all 4 speakers in this session. I really thank you for the effort you have made to participate, to be here, to deliver very interesting talks. Thank you very much. And okay, see you soon.